Welcome back to another video. Let's jump right into the topic of normal distribution. The normal distribution, often called the bell curve, is one of the most important concepts in statistics because it describes how many things in the world behave. It's commonly used to model real-world data like people's heights, test scores, or errors in measurements, all of which tend to follow a similar pattern. The curve is symmetrical, meaning it looks the same on both sides, and is defined by two key values, the mean and the standard deviation. Normal distribution is very practical in statistics because it's mathematically simple to work with. It's used in many statistical tests and methods, such as finding confidence intervals or testing hypotheses. Because the normal distribution can be easily standardized, it makes comparing different datasets much easier. So please pay close attention, as normal distribution is essential because it's so widely applicable and provides a solid foundation for much of the statistical analysis we do in everyday life. It simplifies complex data and is the basis for many statistical techniques used in research, business, and beyond. The normal distribution, often called the bell curve, is one of the most important concepts in statistics because it describes how many things in the world behave. It's commonly used to model real-world data like people's heights, test scores, or errors in measurements, all of which tend to follow a similar pattern. The curve is symmetrical, meaning it looks the same on both sides, and is defined by two key values, the mean and the standard deviation. Normal distribution is very practical in statistics because it's mathematically simple to work with. It's used in many statistical tests and methods, such as finding confidence intervals or testing hypotheses. Because the normal distribution can be easily standardized, it makes comparing different datasets much easier. So please pay close attention, as normal distribution is essential because it's so widely applicable and provides a solid foundation for much of the statistical analysis we do in everyday life. It simplifies complex data and is the basis for many statistical techniques used in research, business, and beyond. The normal distribution is defined by two key parameters. Mean. The mean represents the average or central location of the distribution. It is the point where the peak of the bell curve occurs. In other words, it shows the typical or expected value of the random variable. Variance. Sigma square. The variance measures the spread or variability of the distribution. It tells us how far the data points typically are from the mean. A larger variance means the data is more spread out, while a smaller variance means the data is more concentrated around the mean. Together, the mean and variance fully describe the shape and spread of a normal distribution. The normal distribution is symmetric around the mean, and the shape of the curve depends on both the mean and the variance. While the mean dictates where the distribution is centered, the flattening or thinning of the curve in a normal distribution occurs due to variance. This happens because the total area under the curve must always equal 1. The area under the curve represents the total probability of all possible outcomes, and since probabilities must sum to 1, any change in the width, due to variance, of the curve must be compensated by a change in height. When the variance increases, the curve becomes wider and flatter. This means that while the distribution becomes more spread out, the total probability must still be 1, so the peak of the curve becomes lower to maintain this total area. Conversely, when the variance decreases, i.e., when the standard deviation is smaller, the curve becomes narrower and taller, concentrating more of the probability around the mean. In both cases, the overall area under the curve remains 1, which is a fundamental property of any probability density function. The 68-95-99.7 rule, also known as the empirical rule, is a simple way to understand the spread of data in a normal distribution. This rule tells us how much of the data falls within certain ranges around the mean, central value, when the data follows a bell-shaped curve, normal distribution. Here's what it says. 68% of data is within 1 standard deviation of the mean. If you look at the mean, center of the distribution, and move 1 standard deviation to the left and 1 standard deviation to the right, you will find that about 68% of all data points lie within this range. 95% of data is within 2 standard deviations of the mean. If you extend the range to cover 2 standard deviations, 2 to the left and 2 to the right of the mean, About 95% of all data points will fall within this range. 99.7% of data is within 3 standard deviations of the mean. If you further extend the range to 3 standard deviations, about 99.7% of all data points will fall within this range. The standard normal distribution has a mean of 0 and a standard deviation of 1, making it a special version of the general normal distribution, which can have any mean and any standard deviation. As you may have noticed, unlike the other continuous distributions, we have not yet introduced the CDF of normal distributions. That is because normal distributions don't have closed-form CDF functions where we can get the probability just by simply plugging in the value of x. To standardize a normal random variable, you convert it into a z-score by subtracting the mean and dividing it by the standard deviation. This process transforms any normal random variable into a z-score, which represents how many standard deviations the value is away from the mean. The resulting z-score follows a standard normal distribution, with mean 0 and standard deviation 1. The standard normal distribution is important because it provides a reference point for comparing different normal distributions. It simplifies calculations and allows us to standardize any normal random variable into a standard form that can be used with a table of values or statistical software to calculate probabilities. As the standardization transforms any normal random variable into a z-score, which represents how many standard deviations the value is away from the mean. The resulting z-score follows a standard normal distribution, with mean 0 and standard deviation 1. As shown here, you can see that for random variable x, following a normal distribution with a mean of 100 and standard deviation of 50, the probability of x being less than 150 is the same as the probability of z being less than 1. Similarly, for random variable y, following a normal distribution with a mean of 8 and standard deviation of 2, the probability of y being less than 10 is the same as the probability of z being less than 1. This is happening because in both cases, the threshold is 1 standard deviation above the mean. Reading a z-table is a straightforward process, but it requires some understanding of the structure of the table and how z-scores relate to probabilities. The z-score represents how many standard deviations a data point is from the mean, and as a result, it can be a positive or negative value. A positive z-score indicates that the value is above the mean, while a negative z-score indicates that the value is below the mean. A z-table shows the cumulative probability of a standard normal random variable z being less than a z-value, such as z0. Here you're looking into 3 different z-values of 1, 1.22, and minus 0.42. The table is typically structured with the first 2 digits of the z-score listed along the vertical axis, rows. These represent the integer part and first decimal place of the z-score. The second decimal place of the z-score is listed across the top, columns. For example, if you have a z-score of 1.22, you find the row corresponding to 1.2, the first 2 digits, and the column corresponding to 0.02, the second decimal place. The intersection of the row and column will give you the cumulative probability. So, the probability of a standard normal random variable z being less than a 1.22 is 0.8888. The value 0.8888 means that about 88.88% of the data points from a standard normal distribution lie to the left of a z-score of 1.22. This can be interpreted as the probability that a randomly selected value from a normal distribution with a mean of 0 and standard deviation of 1 is less than or equal to 1.22. You may ask what to do for negative z-scores. The z-table typically provides cumulative probabilities for positive z-scores. To find the probability for a negative z-score, you can use the symmetry of the normal distribution. The cumulative probability for a negative z-score is equal to 1 minus the probability of random variable z being less than the absolute value of z0. For example, the probability of a standard normal random variable z being less than a minus 0.92 is the same as 1 minus the probability of a standard normal random variable z being less than a 0.92, which is 0.1788. Alternatively, we might be given a cumulative probability and asked to find the corresponding z-value. To find a z-score given a cumulative probability, the area under the standard normal curve to the left of the z-score, We just need to reverse the process of reading a z-table. We can start by looking for the cumulative probability closest to the given value in the body of the table, not the margins. Then, we need to locate the corresponding row, first two digits of the z-score, and column, third digit of the z-score. For example, if we are asked to find a z0 so that the probability of a standard normal random variable being less than this z-score is 0.8413, we need to find this cumulative probability in the body of table as shown here, and report the combined values from the first row and column as the corresponding z-score. Here, we report that probability of a standard normal random variable being less than 1 is 0.8413. Please note that if the cumulative probability is greater than 0.5, the z-score is positive. If the cumulative probability is less than 0.50, the z-score is negative. For cumulative probabilities very close to 0 or 1, the z-score will be very large in magnitude, positive or negative. For precise values or large datasets, Python can compute the z-score and cumulative probabilities directly. What if a z-score or cumulative probability is not explicitly listed in the z-table? Then what? If the z-score falls between two values in the table, you can estimate the probability using interpolation. Interpolation involves finding the midpoint or weighted average between the two closest table entries. For example, if your z-score is 1.255 and the table only lists 1.25 and 1.26, you can estimate the probability by averaging or scaling based on how close your z-score is to these two values. Alternatively, you can rely on more modern tools. Modern solutions like Python can compute probabilities for any z-score, even those not listed in standard tables. Please note that if the z-score is extremely high, for example greater than 3.4, or very low, for example less than -3.4, most tables do not include these because the probabilities are near 0 or 1. Here you can see how we can use Python to calculate normal CDFs, PDFs, and visualize them. We can use the norm function to model a continuous normal distribution. In addition to the CDFs and PDFs, we can use PPF function for retrieving z-scores. Here are a few examples on how to find cumulative probabilities and z-scores. Let's go over an example together. It has been reported that new patients pay an average fee of $48 for their first-time office visit to a self-employed physician. Assuming a normal distribution and a standard deviation of $12, what is the probability that a randomly selected new patient pays no more than $65? What is the probability that a randomly selected new patient pays at least $45? What is the probability that a randomly selected new patient pays a fee between $39 and $51? Please pause the video here to take a moment and try answering these questions on your own. We start by finding the z-score to determine how far $65 is from the average fee of $48 measured in standard deviations. To calculate the z-score, we subtract the mean, $48, from $65 and divide by the standard deviation, $12. The result is 1.42. Next, we look up this z-score in the standard normal distribution table or use Python to find the probability associated with it. For a z-score of 1.42, the probability is approximately 0.9222, meaning 92.22% of patients pay no more than $65. Again, we calculate the z-score, this time for $45. Subtracting 45 from the mean, $48, and dividing by the standard deviation, $12, gives a z-score of -0.25. Using the z-score table or software, we find the probability corresponding to -0.25, which is about 0.4013. This value represents the proportion of patients who pay less than $45. To find the proportion of patients who pay at least $45, we subtract this probability from 1, since all probabilities add up to 1. The result is 0.5987, or approximately 59.87%. We need to find the z-scores for both $39 and $51. For $39, we subtract the mean, $48, divide by the standard deviation, $12, and get a z-score of -0.75. For $51, we do the same and get a z-score of 0.25. Next, we find the probabilities for these z-scores using the standard normal table or software. For minus 0.75, the probability is about 0.2266, and for 0.25, the probability is about 0.5987. To find the proportion of patients who pay between $39 and $51, we subtract the smaller probability for minus 0.75 from the larger probability for 0.25. The result is 0.3721, or approximately 37.21%. Thank you for your attention, and see you in the next video.